Welcome back. We're going to talk more about inner products today and also the singular value decomposition. So let's remember where we were. Last time we said, suppose we have a symmetric matrix. We define an inner product from that, which is the inner product of V and W is V transpose AW. And in particular, if V is the vector x1 through xn, then the inner product of V with itself is this thing, x1 down to xn times a times x1 through xn. And if you write that out, you get the summation of the aij xi xj. And we're interested in when this is positive definite, which is to say, when is this number greater than 0 for all vectors v, except for, of course, the 0 vector. And the key example we talked about was the 2 by 2 example, where if you write out, if v is the vector xy, if you write this out, you get the standard quadratic ax squared plus 2bxy plus cy squared. And I want to remind you how we checked this, because we're going to sort of do it again. So what we did is we completed the square, and we saw that we had to have a bigger than 0 and also the determinant bigger than 0. So that was the test for positive definiteness. And the theorem that we stated last time is that the test for positive definite is that the determinants of the upper left-hand corner minors all have to be greater than 0, and there are n of those. We also saw that there's a test in terms of the pivots. All of the pivots have to be greater than 0. And in this example, you see that the pivots of this matrix are, well, let's see, you have A, B. And then in order to kill this B in the lower left-hand corner, you have to use this multiple of the first row. And what you get down here is C minus B squared over A. And indeed, the pivots are A and this thing. And if you multiply this by 1 over A, you see that the condition is that AC minus B squared has to be greater than 0. Fine and dandy. Now, let's look at an example like this, 1, 1, 1, 1. The inner product looks like this, where you get x plus y squared. And I'm asking whether that's bigger than 0 for all x and y, which are non-zero. And, well, let's draw the picture. Here's the x-axis and the y-axis and the z-axis. And clearly this line x plus y is equal to 0 is critical. So let's draw that. This is the line x is equal to minus y, because that's where this length is 0. And if you plot this surface the way we did last time, what you get is the cross sections are parabolas, but it's like a valley. They're all lined up along this line, x is equal to minus y. Not the usual bowl that we saw in a typical case where you get a bowl looking like this. And of course, in this example, the answer is it's not positive definite, because any vector of the form x minus x is 0, but it is positive semi-definite. These numbers are all greater than or equal to 0. Okay, so I want to go on now and talk about positive semi-definite matrices. So the question is, what is a test for positive semi-definite? Well, there's an obvious guess, which is, why not take the upper left-hand corner matrices, these MIs, and the determinants need to be greater than or equal to 0 instead of just greater than 0. Seems like an obvious condition. And let's see if it's correct. So let's look at our 2 by 2 example, a, b, b, c. So we have, again, this quadratic, ax squared plus 2bxy plus cy squared. And as last time, I'm going to complete the square. This is written this way. This is the easiest way to tell whether a number is positive or negative, is by completing the square. We're asking that this be always greater than or equal to 0. Well, clearly, if a is bigger than 0, then you're forced to take c minus b squared over a greater than or equal to 0, not just greater than 0, and that all is fine. So if a is bigger than 0, you also need that the determinant is bigger than or equal to 0. And that's essentially the, that does look like the condition we were just talking about. But, so if a is bigger than 0, it all looks good. But what if a is equal to 0? So then what you're left with is this first term 0, and you have c minus b squared over a times y squared is greater than or equal to 0, and uh-oh, what's going on here? I'm dividing by a, and a is 0, so clearly I can't do this. So we have to go back to the original equation and take a is equal to 0 there. And so the condition is cy squared plus 2bxy is supposed to be greater than or equal to 0 for all x and y. Let's see. How can we guarantee that this is true? Well, if you fix y and let x go to plus or minus infinity, then you can arrange that this number will be negative. All right, this first term is fixed, and just take the second term to minus infinity, and you lose. So, what does that say? The second term is bad. You basically lose if it's there, so that forces b to be equal to 0. And then cy squared, of course, is greater than or equal to 0, says that c is bigger than or equal to 0. So the conclusion in this case is the following. When is this matrix positive semi-definite? Well, the first case is if it's positive definite, which of course means that a is bigger than 0 and the determinant is bigger than 0. And the second case is if a is equal to 0, which forces b to be equal to 0 and c to be positive, or sorry, non-negative. And it's this matrix here, 0, 0, 0, c. And similarly, if c was equal to 0, you'd conclude that a has to be bigger than or equal to 0. And in particular, there's the following telling example, 0, 0, 0, minus 1. Notice that the determinants of all the mi's are greater than or equal to 0. You have a 0 in the upper left-hand corner, and the determinant of the whole thing is 0. But it's not positive semi-definite. So it's definitely not enough just to check the mi's. Okay? You should think about this example carefully to see. It's not enough to check. We need some more information. And here it is. If you have an n by n matrix, a principal minor of an n by n matrix, a principal submatrix of an n by n matrix is the following. You remove some collection of the columns, some set of columns, and you remove the matching set of rows. And then you take what's left. So, for example, if you remove the second column and the second row, you get this matrix ACGI. Another example is you could remove the first column and the first row, which leaves EFHI. And a third possibility is you could remove the first two columns and the first two rows, which leaves this matrix I. So those are the examples of the principal submatrices of a given matrix. And the condition is that all of those determinants have to be bigger than or equal to 0. So here's the theorem. A matrix is positive semi-definite if and only if the following conditions hold. Each of these conditions is equivalent. Any one of these conditions is enough. So first of all, this number v sub a is supposed to be bigger than or equal to 0 for all v. That's the definition of positive semi-definite. And all the eigenvalues need to be greater than or equal to 0. The determinants of all of the principal submatrices have to be greater than or equal to 0, or principal minors. And all equivalent. Another one is that all of the pivots have to be greater than or equal to 0. And let me just remind you that the key example you should keep in your mind is this one, which tells you it's not enough just to take the upper left-hand corner matrices to check. And the way this is detected here is when you remove the first row in the first column, you get this -1, which tells you that this matrix is not positive semi-definite. Okay, that's enough of that. Let's go on to the notion of singular value decomposition. So remember, if A is a matrix, we are interested in writing it as QD transpose, where Q is orthogonal. Now, of course, you can only do this if A is symmetric, because the matrix QD transpose, if you take its transpose, it's automatically symmetric. So, and we know that if A is symmetric, it has a decomposition like this. And the question is there an analog of this for non-symmetric matrices? Well, let's see. Maybe a silly thing to try would be, what if you allowed a different orthogonal matrix on either side? What if I tried to write A as QDR transpose, where Q and R are orthogonal but not necessarily equal? I don't know. Let's see. How do you tell if this is plausible? Let's see if we can get any information about this and do some guessing. So for example, what would D have to be? In the case of a symmetric matrix, D is the eigenvalues, the real eigenvalues of the symmetric matrix A. And I'll remind you that the reason is QD transpose is the same thing as QD inverse, and that's a similarity transformation which preserves eigenvalues. So what's going to happen now in this more general setting? Well, let's see. If A is QDR transpose, notice what A transpose is. It's QDR transpose times QDR transpose, which is to say QDR transpose, R D transpose, which is D Q transpose. And by definition, this R transpose in the middle, that's a misprint. It's R transpose R is equal to the identity. And you get Q D squared Q transpose. And this AA transpose is symmetric. And in fact, it's positive semi-definite. And so that tells you something about D. Since D squared, this is the symmetric case, and so the eigenvalues of D squared are the eigenvalues of AA transpose. That is to say, D has the square roots of these eigenvalues on the diagonal. Okay, so you take A, you compute the eigenvalues of AA transpose, take their square roots and make them put them in D. And you also see from this equation up at the top that the matrix Q is made up of the eigenvectors for this matrix AA transpose. That's the standard thing when you're doing this for a symmetric matrix. And if you do things in the other direction by symmetry, you see that R is made up of the eigenvectors of A transpose A. Okay, well, it turns out that this is all true. Excuse me, and in fact, it's even true for non-square matrices A. This is quite remarkable. So let's see what this means. So you have this matrix A, which is M by N. And I want an orthogonal matrix, which is M by N, and another orthogonal matrix, which is N by N. So when I do this multiplication, I get this matrix A, which is M by N, and this matrix here in the middle is supposed to be diagonal. Well, what does diagonal mean for a non-square matrix? Well, it looks like this. It's a little square diagonal matrix and then some zeros. Okay, so let's see. We have A is an M by N matrix. So let's go back and think about this in terms of maps between vector spaces. So you have a map from Rn to Rm. And if I were to write A as QD R transpose, what would that mean? Well, the first thing I would be doing is taking R as a map from Rn to Rn. That should be R transpose. And then D is a map from Rn to Rm of this very simple form, either like this or like this, depending which is bigger, M or N. And then finally, I'd be applying this matrix Q going from Rm to Rm. That's the idea. And so here's the result, the singular value decomposition. The statement is the following. Suppose A is any M by N matrix. Then you can write A in the form QD R transpose, where Q is M by M symmetric, orthogonal. R is N by N orthogonal. And D is M by N diagonal. And I put diagonal in quotes because it's as I explained on the previous slide. And the entries of D, these diagonal entries, are exactly the square roots of the eigenvalues of A transpose. Furthermore, this matrix Q is constructed as follows. You take the vectors v1 through vm, which are the eigenvectors for A transpose, and put them in the columns. And similarly, you take R to be this matrix where you take the n vectors w1 through wn, which are the eigenvectors of A transpose A. Pretty neat, if you ask me. Okay, so let's look at an example. Do a very small example. Suppose A was this little 2 by 1 matrix, 1, 2. So M is 2 and N is 1. So we're trying to write it as a 2 by 2 orthogonal matrix times a 2 by 1 diagonal matrix, which means 0 and something in the first coordinate, followed by a 1 by 1 orthogonal matrix, which is to say, obviously, just a scalar. Okay, so let's compute these things. Well, D is this thing D0, where D squared is the eigenvalue of A transpose A, or AA transpose. Well, let's compute those two things. A transpose is when you multiply this times this, you get the matrix 1, 2, 2, 4. And let's compute the eigenvalues of this thing very quickly. What you get is lambda squared minus 5 lambda plus 4 minus 4 is equal to 0, which is to say lambda is equal to 0 or 5. And we're interested in the non-zero one, which is 5. And if you compute A transpose A, you get the scalar 5. So that has one eigenvalue, 5. So D is 5. Excuse me, the square root of 5 is the conclusion. So let's put that in here, and another misprint, unfortunately. That's 5 supposed to be the square root of 5. And let's see, R is supposed to be 1 by 1 orthogonal. So, well, it's 1. And what is A? A is supposed to be the eigenvectors of this matrix put into columns. And it's easy to see what the eigenvectors of this matrix are. The 0 eigenvalue is, the 0 eigenvector is what? It's minus 2, 1. And the 5 eigenvector is 1, 2. So you scale those to make them length 1, and you see that Q is this matrix. 1 over radical 5, 2 over radical 5, and minus 2 and 1 all over radical 5. And the conclusion is that you take Q and you multiply it times this diagonal matrix, which is a radical 5 there, and 1, and when you multiply this out, you get 2, 1. Okay, that's a good place to stop. See you in class.